So, speciation happens, and there's species all over the planet that show us this, and things that are slightly different, like the sea turtles versus the tortoise. Those are all different, and that's great. But I can hear your minds whirring right now. Okay, what about different groups of animals that do interbreed, like hybrids? For example, you guys know all about mules, right? Mule is probably the most common hybrid around the world. What is a mule? It's a donkey and a horse interbreeding. All right, all right. How, if donkeys and horses are different animals, different species, why can they interbreed? And, well, the answer is complicated. But we'll talk about it. It really all has to do with time. Everything in this has to do with time and those generations. Fundamentally, if there is a hybrid species, not enough time has passed for them to fully speciate. In other words, they're still compatible to some degree. Check this out. Oh, finally, fun pictures. What the hell is this thing? Looks like the head and front end of a zebra on the back end of a horse. And you're right, it's a zorse. Is this zorse in its natural habitat? You probably are instantly saying no. But in fact, it is in its natural habitat. It's in a zoo, a horrific zoo from the look of it. But this is what people do. We take horses and zebra and try to see if we can interbreed them to act as a tourist attraction in a given zoo. Thankfully, they're doing this less and less often. In fact, no zoos in the United States will participate in this horrific, cruel thing anymore. All right, so why not? What's going on? Well, the zorse, made up of zebra and horse. Where do zebra live? Where do they come from? Africa, the plains of Africa. What about a horse? That's a little harder question. Most horses are from the Arabian Peninsula, up in the northeast of the Arabian Peninsula, and up through Western Europe and Central Europe. That's where horses come from. So, do they ever see each other in real life? No, they don't cross paths. There's deserts and oceans in between them. So, they were at one time fairly closely related. In fact, you can look at a horse and look at a zebra and figure that out. They're all running around on one toe. That's what the hooves are, by the way. A hoof is a single toe. The rest of their toes are up in there, but they're all squished up in there inside the leg. So, zebra and horse, they can interbreed because not enough time has gone by for them to fully speciate. This is what we call reticulation. Don't worry about it. It's not a big word that you need to know, but reticulation means that they're still within that speciating period. Remember, for us, it takes 1,000,000 years, which we haven't even lived long enough to do that. But when they start interbreeding, that breaks the reproductive isolation. When somebody brought a zebra over to a horse and they interbred and produced this, there you have a hybrid species, and you have reticulation, and you have the cessation of reproductive isolation. So, why is this such a horrific practice? Because of what happens to the animal. If this animal is in fact not sterile, which is common for hybrid species to be sterile, meaning they cannot sire children, they can't become pregnant or get anything pregnant. The other thing is they tend to have organ failure issues. They tend to die very, very soon, very, very young. The zorses, died usually within about the first year. So they would breed them, let them live for as long as they could possibly hang on, and draw in as much tourist dollars as they could. Pretty cruel practice. But wait a minute, what about our favorite one? If you're a fan of Napoleon Dynamite, remember that movie? It was way back in the 90s. The Liger. Before you ask, yes, this is photoshopped. It's not a real liger. Most ligers didn't look this impressive. In fact, most were females, so they didn't have a mane at all. And those that weren't, they were very sickly. Same reason. The ligers, and we did make ligers, even here in the United States, we made ligers at various zoos, but the ligers only lasted maybe 2 to 3 years tops before they died of multiple organ failure. Because remember, this is two relatively incompatible genetics. You've got a lion and a tiger trying to interbreed. By the way, it was artificial insemination. Lions and tigers, if they were to be near each other, one would kill the other. They're pretty not compatible animals. But this is a typical thing that people would do. We do this a lot to a lot of different things. By far the most successful species we've ever interbred was the mule. And we'll explain that and all of these other things with kind of an intense rule. Bear with me here. This is Haldane's rule, and I know you're itching to do it, but don't write this down, at least not yet, because it doesn't make any sense if we read it the way it was originally written. Let's read it together. I just assume this is what Haldane sounded like. When in the offspring of two different animal races, he meant species, or in fact, breeds. One sex is absent, rare, or sterile. That sex is the heterozygous or heterogametic sex. What the hell does that mean? That's why I didn't have you write it down. Let's work it backwards and figure out what Haldane was saying. When two get together, the heterozygous or heterogametic sex, which sex is heterozygous? Remember your Punnett squares? Which one is heterozygous? Male, XY, remember? So the XY is heterozygous, therefore the male, we can take out a heterozygous, heterogametic, and sex, just put in male. The male is sterile, rare, or completely absent. What is he saying? That if not enough time has gone by and you get two speciating individuals, in other words, if that 50,000 generations has not taken place, if it's at about 25,000 or less generations in general, about halfway mark. Remember, we're talking generations, not years. If half that time has gone by, then they can get together and they will do one of three things. They will either not produce babies at all, they will produce a baby, but if they do produce a baby, it will be either sterile or always female. Does that make sense? So, let's take it back to our favorites, the mule. The mule, remember, is a horse and a donkey mixed together to create a mule. Can mules sire mules? Could two mules get together and make a baby mule? No, because Haldane's rule has taken effect between horses and donkeys, meaning about 25,000 generations or less, somewhere in that 20,000 range, have gone by. Therefore, they can still interbreed and make babies, but they cannot. The mule and the horse can interbreed and make babies, but those babies cannot go on to make more babies. Does that make sense? Now, mules are probably early on in that scale, before the 25,000, something like that. So they're healthy. Unlike the liger and the zorse, the mule is a fairly healthy animal. They live a long life. They're strong, but they're sterile. So Haldane's rule has started to take effect. After that, all of them will be sterile. And then at about 50,000 generations, they won't be able to make babies at all. Does that make sense? Haldane's rule is probably one of the tougher things to fully grasp. This and Punnett squares are up there. However, hybrid speciation does in fact happen. If you look at this picture, it looks kind of like a wolf, kind of like a coyote, and you guessed it, it's a coyote wolf, also known as the red wolf or Canis rufus, which means red wolf, or red dog, really. Canis rufus. These little guys are made by wolves, timber wolves in this case, and coyotes being too close to each other. And again, that's humans doing it. Not that we're getting together to make these things, but we're putting up Walmart and things like that. We're taking over their hunting ground, especially the wolves. So the wolves are being forced down, and the coyotes are being forced up, and so finally they meet in the middle. Now, wolves and coyotes normally don't get along very well in nature. Coyotes are usually considered by wolves to be lunch. They're much smaller than wolves. Wolves will usually attack and eat coyotes if they're in the area. Coyotes, on the other hand, are usually hunting things like rabbits, smaller game. So the fact that humans creating the cities and buildings and all this stuff, that we take over their land, we sort of force them, these two populations that normally would be very separate and have been for thousands and thousands and thousands of years, we're pushing them together. But this is the exciting part. A wolf and a coyote get together and make this thing. This is called a red wolf. It is called a hybrid species because they live long, healthy lives and they are not sterile. Meaning, really, Haldane's rule is nowhere near in effect. Haldane's rule takes effect somewhere around 20,000 generations, remember? This is much earlier than that, probably at the 3,000 or 4,000 generation mark. So what we have here is a third species created by two other species. It's called a hybrid species. There's one last little thing to comment on, and that is homoplasies, which can get confusing when we're trying to determine who's related to whom. I mentioned earlier the horse hooves and the zebra hoof, and the fact that those are really just fingers. Their hoof is actually fingernail material. That's what makes up the horse's hoof, is fingernail. Two similar traits arising independently in two non-related species is called a homoplasia. We see these all the time. That is, two things that have never been very closely related, that come up with a similar, if not the same, means of something. Usually it's getting around. The most classic example of a homoplasy, homo means same, plasy means shape, same root word as plastic. Homoplasy, same shape, is coming up independently. That's important. The most common example of this is the bird wing and bat wing. Birds are birds. They're not mammals, are they? Mammals don't lay eggs. Humans are mammals. We don't lay eggs. We're not covered with feathers. We're covered with fur or hair. We have live birth, and most importantly, where we get our name from, we have mammary glands. We nurse our young, right? The females of our species nurse babies. Well, bats are also mammals. They're covered with fur, not with feathers. They also nurse their babies, and they also deliver live young. They don't lay eggs. A bird has two wings. A bat has two wings, and they fly around very similarly. But there's a lot of very different things going on. First of all, let's look at the bird wing. If we look at the bird wing, we see this upper arm bone, which, just like our upper arm bone, is called the humerus. Bat's got the same arm bone, humerus. Then the bird has the forearm bones, the radius and the ulna, just like humans. The bat has forearm bones, the radius and the ulna, just like human beings. The bird has the carpal bones and metacarpals that make up our hand and wrist, and it's got phalanges stuffed in there too, little fingers. But what makes up the majority of the bird's wing is feathers, which we now know, after watching Jurassic Park, they're modified scales. from dinosaurs. Great. What about the bat wing? Well, we got to the radius and ulna. Up here, the carpals and metacarpals. But now the phalanges, the finger bones. Look at what's going on. They're stretching all the way down, and there's this flap of skin stretched between them. That's what makes up the bat's wing. Same bones, different shapes, different functions. The bat wing is supported by those little finger bones in there, except for its little hitchhiker thumb up top. So bats and birds, while they look similar, if you were just to look at them and be like, hey, there's two flying objects in the sky there, and they both have two wings, they're actually very, very different. This is a classic homoplasy. Now that I've commented on these, you can probably think of thousands on your own. Think about things like a butterfly wing, a bee wing. Wings go on and on. Legs. Think about a caterpillar's legs compared to a human leg, or a horse's leg, or a goat's leg. All of these animals have legs. In fact, think about how many four-legged animals there are that are not related. Goats, dogs, cats, lizards, goes on and on and on. I think you get the point. These are all homoplasies. What's the whole point of this? Well, remember when we talked about Linnaeus and trying to figure out a taxonomy? Taxonomy goes along hand in hand with something called cladistics. And cladistics is a way of understanding who's related to whom. I associated taxonomy a long time ago when we were talking about Linnaeus with a family tree. A cladistic is the same thing. Cladogram is a family tree. And I want you to think about it like we do in things like, you might have learned this in geometry, where they say all squares are rectangles, but not all rectangles are squares. There's a directionality to that. There's a hierarchy. Let me explain using the boxes up top here. Do you see I have a big gray box on the outside? Big gray box labeled mammals. Inside that is a beige box named primates and a green box named apes. So, are all apes primates? Yes. Are all primates apes? No. You've got monkeys, you've got prosimians. They're not all apes, but all apes are primates. You see that directionality there? Mammals. Are all primates mammals? Yep. Are all mammals primates? No. Dogs, cats, not primates. Does this make sense to you guys? There's a directional flow here. Now, if we put that into terms like this down here, A, B, C, and D. Do you see these? These are supposed to line up with these bars, but they don't when I switched over, whatever. Okay, so everybody in this entire group here, A, B, C, and D, are all mammals. Let's say A is human, B is chimp, C is, I don't know, we'll call that a baboon. C is a baboon, which is a big monkey. And D, we'll call that a dog. So, A is human, B is chimp, C is baboon, D is dog. Everybody going along with this so far? So all of them are mammals. A, B, C, and D are all mammals. A, B, and C are all primates. Humans and chimps are both apes. By that, I can say humans and chimps share a more recent common ancestor than do baboons and dogs. Dogs are the furthest out. You can think of this just like a family tree. If A is you, B is your sister, you share your parents. If C is your cousin, you share your grandparents. If D is your second cousin, you share your great-grandparents with that person as far as a most recent common ancestor. Do you see the directionality here? We can determine who's closer related to whom using a cladogram. Now, the cladogram normally doesn't have the boxes. It would just be these sticks, just so that you know. It's called a cladogram. Cladograms are, you'll hear cladistics, that is determining close relations. So the cladistics, for example, between a mule and a horse, a donkey and a horse, cladistically, would be closer than a zebra and a horse. Does that make sense? You could do the same thing. You could make A and B. A could be the horse, B could be the donkey, C could be the zebra, and D could be, I don't know, a tiger. All of those are mammals. The tiger is clearly far separated from these three, and we know just by their survivability that zebra are not nearly as closely related to a horse as the donkey is. Does that make sense? It should. Cladistics are all based on who's related to whom. That's the take-home message there. And all of this is based on something that came from another guy who's in the clergy. William of Ockham. Ockham is a small town, still is, in sort of north-central England. William of Ockham, who was a monk, which you can probably figure that out by looking at him, was in a big consortium of thinkers. He was a philosopher working within the church in the 1200s. Basically, he was right around the end of the 13th, beginning of the 14th century. He was a group of people trying to figure out some ideas like that were related to the Bible, trying to answer some questions like how many angels can dance on the head of a pin is the famous one that you hear about a lot. They were literally trying to figure out, okay, how big is heaven? How large is it? How would that work? They were kind of coming up with these philosophical answers to the letter of the Bible. Well, like all monks, he wrote it in Latin, but he wrote the Lex Parsimoniae, which means basically the law. Lex means law, the law of parsimony, or the law of making things make sense. That's kind of what it means. We now call this Occam's razor, and I'll go on my rant about why that is in just a second. But razor is Old English for law, or, yeah, that's the best term for it, rule or law. His Lex Parsimoniae, law of parsimony, said, all other things being equal, a more simple explanation is preferable to a complex one. A more simple answer is probably the correct answer. That's what he's saying. All other things being equal, the simplest answer is likely the correct answer. This comes up all the time in science. It doesn't come up too often in real life, but let me give you an example in everyday life that probably would help you guys make sense out of this. Do you guys remember the crop circles that we talked about during the end of the pseudoscience talk? Well, the crop circles, you can believe one of two things. You can believe that extraterrestrial spacecraft came to town and quietly didn't talk to anybody, instead made weird circles on the ground in crops and then flew off. So they spent millions of years trying to figure out interstellar travel, figured it out, got here, which takes another probably a couple thousand years of flight, assuming they're not bending space and time and all that, whatever. They figured all this out, and all they wanted to do is make cryptic circles on the ground. Or it was two drunk guys and a rope. What would William of Ockham say? Which one's the simpler answer? Two drunk guys and a rope. So that's probably the right one. Now, we use this all the time with cladistics, trying to figure out who's related to whom. And I just threw one out, and you guys all accepted it, I think, by the way it sounded. Remember the last one I threw up? And I said the tiger is the outlier there? And everybody kind of agreed, because if you look at donkeys, zebra, and horses, they all have hooves. They all have a look. They look very similar. How come? Well, there's too many dissimilarities between a tiger and a horse to make it seem like they're probably very closely related. Conversely, zebras and donkeys look very similar to a horse. So applying Occam's razor, as we all did in our minds when I gave that example, you kind of already know the outlier is going to be the tiger. That should make sense. Now, the reason they call it Occam's razor, I swear to God, is because old, boring people can stand up in the middle of a talk some person's doing and say, I think you're cutting yourself on Occam's razor. That's the only reason that stupid, long overused joke is the only reason that in science today we still use Occam's razor. It's the only thing we ever use Old English for in most things in science. Everything else would go law of parsimony. But no, Occam's razor, you can make that stupid ass joke, and people do ad nauseum. I'm telling you, it's crazy to me. But that's what Occam's razor. By the way, nobody really knows how to spell Occam. It's OCCAM, OCCHAM, OCKHAM, OCAM, OCKAM. There's a million ways of spelling it. It's because everybody was illiterate in the 12th century, except for the monks anyway. So there you go. Okay, so hopefully this ties together speciation, hybridization, and homoplasies and cladograms to a fairly comfortable place for you.